Hello and welcome to Embedded System Design Techniques, Episode 1, Introduction to Bootloader Design for Microcontrollers. I'm Jacob Beningo, and I will be your host and lecturer for today's session. Now this episode is the first in a series of webinars for subscribers of my free monthly Embedded Bytes newsletter. The newsletter provides individuals interested in developing embedded software articles on the fundamentals of software concepts, tips and tricks for developing firmware, guidance and recommendations on tools, industry trends, along with other useful resources. This webinar is an example of one of those resources. In order to find out when the next free webinar will be held, please visit www.beningo.com and consider signing up for my free newsletter. Today we are going to be discussing fundamentals of bootloaders. Now, bootloaders are a tool firmware engineers use to update their system software without the use of any specialized tools such as JTAG programmers. In today's session, I'm going to provide you with an introduction to bootloader design. We're going to be looking at the fundamentals of the bootloader system. We're going to examine some of the different types of models that can be used to develop a bootloader. We're going to look at the different pieces that are involved in the bootloader system, how they interact with each other. We're going to take a good detailed look at the startup branching code. This is going to be code that decides whether the bootloader should be updating the firmware on the system or whether the application code should be running. We're then going to examine the typical bootloader behaviors. How does the bootloader parse a new application? We're then going to look at how we can reset the system once we've updated the firmware. And then we'll take a look at memory management within the system. This is going to be making decisions as to where the bootloader code should reside in memory and where the application code should reside. And then finally, we're going to take a look at the different types of formats that our application code can be placed in before sending it to the bootloader. Now, before we get started, let me give you just a brief introduction about my background so that you have an idea where I'm coming from. I'm Jacob Beningo, the President and Principal Consultant of Beningo Engineering, also known as Beningo Embedded. I started writing embedded software in the late 1990s with my first microcontroller being a microchip PIC16F84, and the firmware being written exclusively in assembly language. Since that time, I've had the opportunity to work on over 50 embedded systems projects, spanning industries from automotive all the way through space systems. If the electronics have a microcontroller in it, then it's right up my area of expertise. I started Beningo Engineering back in 2009 with the intent of helping companies and engineers develop robust firmware at an affordable cost. There are three ways I help the embedded software industry, engineers, management, and firmware enthusiasts. First, I perform consulting services such as software architecture design, code analysis and review, process improvement, and secure firmware development. Second, I write and speak about embedded software design techniques. I've written hundreds of articles about firmware development between my blogs on Beningo.com, Design News, and EDN. I am also a regular speaker at the Embedded Systems Conferences and ARM TechCon. Finally, I also teach a number of firmware-related courses and workshops ranging from basic introduction to C programming courses all the way through advanced workshops such as hands-on bootloader design techniques courses. For more information about what I do and also the free firmware resources that are available, please visit my website at www.beningo.com. In the meantime, let's get started with today's session. Now, today's session is all about bootloaders. And as I mentioned in the first slide, a bootloader is a piece of software that we're going to put on our microcontroller that's going to allow us to update our firmware in the field. Now, why would we want to do this, you might wonder? Well, if you think about it, one, JTAG programmers can be extraordinarily expensive. If we had to go and purchase $1,000 JTAG programmers for every technician that's going to go out in the field to update firmware, it could get really expensive very quickly. Secondly, having to have someone that goes into the field and manually update software and open the embedded system, that could be very costly and very time consuming. So when you start to think about bootloaders from today's standpoint, we're starting to get into this era of the Internet of Things where every piece of embedded software is connected to the Internet. And by being connected to the Internet, we're going to have billions of microcontrollers out on the web that are going to have their firmware updated. And the Internet provides us with that medium to be able to transmit new firmware updates to update our embedded systems in the field. Now, why is a developer going to want to update their firmware? There's a couple of different reasons. One, many developers are short on design time. So they have a whole bunch of features they need to get into their product, and they don't have the time, so they're rushing to get a product to market. So what ends up happening is they end up cutting features out that really need to be in the product. They get the product shipped. They want to be able to add features over time. Now, there is also a problem that because they were rushing, they've probably introduced some software bugs that didn't really rear their head during testing. So in order to be able to get rid of those bugs, they have to be able to update their firmware in the field. And the best way to go about doing that is to use a bootloader. Now, as I've mentioned, a bootloader is basically an application whose primary purpose is to allow a system software to be updated without the use of a specialized hardware tool such as a JTAG programmer. A bootloader can also be considered to be a piece of software that boots the system into a known state and can then make a decision on how it should boot from that standpoint on. For our purposes today, we're considering the bootloader to be that piece of code that's going to update the application code in the field. One of the questions that might come to mind is, where can I go out and get a bootloader? And there's really 4 different places that we can get one. First, we can look at our chip manufacturer's website and see if they've provided us with a bootloader by default. Sometimes the microcontroller vendors will produce a bootloader. They'll provide some example code. The problem is that a lot of times their example code tends to be very functional. It's not designed to be in a production environment. So if we're doing rapid prototyping, the code provided by the chip manufacturer may be absolutely perfect. But if we're expecting our bootloader code to be able to work on the moon or in very harsh environments, maybe at high altitudes, maybe in a safety critical system, then the code provided by the silicon vendor really isn't going to be our best choice of bootloader code. Our second option is to look to a third party. There are a number of third parties out there that will develop bootloaders for you. Basically, you provide what your requirements are, and then they will take those requirements and develop a robust bootloader for you. I, for example, have developed dozens of bootloaders for clients over the last 5 years. I've gotten so good at it that I actually have nice clean APIs and a toolkit associated with it that help me very rapidly develop a robust and secure bootloader. Now, the third source is going to be to go and look at open source software. It may be that perhaps some platforms such as Arduino or other open source libraries have provided ways to perform firmware updates. You can take a look at that code and maybe be able to integrate it into your system, but once again, when it comes to open source, the code that you're getting probably isn't of a very high quality. It's very functional, but it's not meant to be used in a production environment. So you have to look at it very carefully, put it through all of its paces, and then you also have to be concerned then about the licensing agreements that are associated with that open source code. It may be that if you use that bootloader or modify it to use to be able to update your application, you may end up having to release a whole bunch of code that you didn't want to, just in case you didn't properly read that licensing agreement. So you have to be very careful about the open source code. Then finally, the fourth option, which is the option that we're mostly going to focus about in today's session, is how to create your own bootloader. And in this case, we're literally starting from the requirements phase, and we're going to be designing a bootloader from scratch so that we can update our firmware in the field. So let's take a look at some of the different bootloader models that we may want to base our bootloader system on. The first model, and kind of the more traditional and most common, is a single microcontroller system based bootloader. In this type of system, we have our primary embedded system with a single microcontroller, and we're going to physically connect either a workstation, a laptop, or a tablet to it, and we're going to be in physical proximity to the embedded system. So this would be something along the lines of, I want to update firmware in my vehicle, I'm going to walk up to my automobile, I'm going to connect something to it, and I'm going to update maybe an ECU that's on board. I'm physically getting access to that embedded system to update the firmware. So in this case, we're going to have some software on our embedded system that's going to be able to read in new application packets. We're then going to have some type of GUI on our tablet or on our workstation. This GUI is then going to control the firmware update process. It's going to go and tell the embedded system, hey, I want to update firmware. The system's going to respond and say, okay, send me the new data, and then the new application is going to be downloaded to the system. So it becomes very transactional, and we end up being in very physical proximity to the system. Now, the second type of bootloader system that we might consider is one in which we've broken the embedded system up into multiple microcontrollers. This is something that you might see inside of a safety critical system. You may have a master microcontroller, which is going to be doing most of the work, and that is then has a number of slave MCUs connected to it. The slave MCUs are maybe connected through I2C or SPI bus, maybe LIN. Then what we end up happening is that we have a bootloader on each of the slave MCUs as well as the master MCU. We then perhaps have the same type of environment where we're going to walk up with a workstation, a laptop, or a tablet. We're going to physically connect to the master microcontroller. We can then have the opportunity to update the master microcontroller or to have the master microcontroller act as a pass-through so that we can update the firmware on the slave devices. This is a little bit less common of an architecture, but you would potentially see this in some type of safety critical system where you have the main microcontroller that's performing the work, and then you have safety microcontrollers watching the behavior of the master to ensure that it's doing what it's supposed to. In that case, we're probably going to have to update firmware on all these different devices, and this is one way in which we can architect our system. Now the next model, and the one that is a little bit more interesting to us perhaps, especially in the age of the IoT, is we're going to have all these embedded systems that are connected to sensors, connected to Wi-Fi, or over cellular, and they're able to connect directly to the internet. Now, if these systems are able to connect directly to the internet, we probably don't need to get in physical proximity to them anymore. So we're not going to be physically located near them. These sensors there could be billions of them scattered throughout the world, and they're directly connecting to the internet. And what we're doing then perhaps we could be using a workstation or a tablet, but more likely we're using some type of server-based system which has the ability to push updates out to the individual devices, perhaps in batches. And the idea is that we're then able to have the embedded system directly connect through the internet to some type of server or update tool that is then going to architect and guide the firmware update process. So it could be that we're going from the server side, pushing firmware updates down, or it could be the individual systems are periodically going up and saying, hey, do you have any new firmware for me? And then they're updating themselves. So in this type of model, we have the internet, the cloud, our embedded systems. We have the cloud piece over here, and then we're pushing firmware from the cloud down into the embedded system. But they're directly connected to the internet. Now, in a second type of internet-connected system, we're starting to separate the embedded system a little bit. Perhaps we didn't have the money or the way in which the embedded system had to be designed. It didn't make sense to connect it directly to the internet. Perhaps there's some safety concerns or some security concerns with connecting directly to the internet, maybe some type of medical device. So what we're going to do instead is take our embedded systems, maybe we're connected over Zigbee or Bluetooth or some type of wireless protocol. Instead, we're going to connect directly to a server. And this server is going to manage the update process. So this server may periodically go out through the internet, get the latest firmware, or be pushed the latest firmware, and then at the right time, when it decides it's a good time to update the firmware, it's going to push the update down into these different systems. So these are a couple of different common models that could be used for developing a bootloader architecture for the embedded system. Before we start to develop a bootloader, there are 7 key areas that we need to think about as far as requirements are concerned. The first is we need to think about the switch operating mode. And what I mean by this is our system, our bootloader, and our application, they need to be able to switch from the bootloader to the application and from the application to the bootloader. Because really what we're going to be doing is running our application code. That's what we've designed the system to do. But at some point, the application is going to get told that it needs to load the bootloader. So there has to be some mechanism to switch between running the application code and jumping to the bootloader code. Now, one common way to do this is to use either an EEPROM byte or a flash byte, and you set a certain value in that area, and then you restart the system. When it boots up, it then checks that area and makes a decision as to whether it should switch on the application code or stay in the bootloader code. Now, the second area that should be considered is the communication, and more specifically, the communication interface requirements. So this is going to be, am I going to update my firmware over USB? Am I going to update it over CAN? Maybe I should use I2C. Pick your communication protocol of choice, and that's the one that is most likely going to go there. The third option is going to be record parsing requirements. There are a number of different ways that we can store new application data. We could store it in S records, in hex file formats. We could use Intel formats. We could encrypt the data format. We could perhaps have S records that we encrypt and then send packets across. We need to make a decision what type of application format we're going to use up front so that we can design our protocol safely around it. So that's another area we want to consider. We then want to consider the requirements for the flash system. These are going to be simple requirements like the ability to erase the certain areas within the flash space. Maybe be able to write different areas, read different areas. Those types of requirements. Those same flash requirements are also going to be required for the most part if you have an onboard EEPROM. If you don't have EEPROM, then the fifth area isn't of any concern. But if you do have it, you need to ask those same questions. How is EEPROM going to be partitioned? Are we going to be able to erase it, to read it, to write it? Maybe there's configuration structures that need to be developed to store calibration data at startup. Those are the types of things we need to be considering when we're starting to figure out the requirements for our bootloader. We then also have a sixth area for the robustness of the bootloader. Is this just a very simple application that we just need to be able to update the firmware? Maybe we can perform a mass erase of the entire embedded system and then update the firmware. And if it crashes, no big deal, you just restart it and you start the update process again. Then again, maybe it's a safety critical system that's being updated on the fly. In which case, we need to make sure that if the firmware update process fails, the system's able to recover and that nothing goes wrong as far as a safety aspect of the system is concerned. So we have to define what the robustness requirements are of our bootloader up front. And then finally we have, related to that, our seventh area, which is security. Do I need to encrypt my bootloader? Do I need to provide digital signatures? We need to think through how we're going to protect the bootloader, such as locking down flash space, having security keys. We got to consider all these different areas when we're putting together our bootloader. Let's walk through an overview of the bootloader system. We're going to do this from two different perspectives. The first is going to be a system state diagram. In this case, this is going to be our bootloader's primary embedded state chart. We're looking at a very simplistic bootloader here. So what we're going to do is we're going to power on our system, we're going to initialize it, and our system is going to move into a run state. So this state chart is basically showing us the different possible states that our embedded system can be in. So we have a normal run mode, where we're going to be running our application code just like we normally should. We may have a diagnostics mode that we can move into and out of in order to perform debugging. We may have the ability to move into a low power sleep mode and move back to normal mode. Really, for today's purpose, what we're most interested in is being able to move from our normal mode into a programming mode, and then using that programming mode to update the firmware, and then moving through a power on reset process where we can then move back into the normal mode. So there's a couple different ways that we can think of this bootloader. We have a bootloader in memory. We have an application code in memory. We're going to have to somehow switch from one to the other. The cleanest way to make sure that we're able to do that is to use a power on reset to update the firmware. So we may go from normal mode, which is our application code, into the program mode. Power on reset will force us back in the system init. If we set some byte to force us into the application code, then when we initialize, we'll end up back in our normal mode. If we were in normal mode and we want to switch to the program mode, maybe we set some byte in memory, move to the power on reset, move through system initialization again, and then we end up into our program mode when we enter into our primary run state. Now, this behavior can be seen a little bit better in more of a generic flowchart type of perspective. Now, what we have is the embedded system starts up. So we start here at this dot. We move into what's known as the branching code. So this is going to be decision-making code. It's going to decide, should I run the application code or should I run the bootloader? Based on that decision depends on what branch it's going to take here. So if we said this is normal operation, we want to run our application code, we move in, we load the application, we just sit here and run the application code. Periodically we check to see, hey, is there a request to enter the bootloader? If there ever is, we set that byte or whatever behavior we want, and we move through that software reset that then forces us to restart the system, come back into our branching code. The code decides, should I load the application or the bootloader? In this case, since we told it that we wanted to start the bootloader, we're going to move into the bootloader code. In which case, we initialize the bootloader, and we're going to wait for commands that allow us to update the firmware. When those commands come in, maybe it's something like erase a partition in flash, maybe it's program a certain page within flash space. We're going to execute these commands until all of the firmware locations in flash have been updated, and we're told that we can exit to the application. At which point we go back to that software reset and then back to the branch code, which makes that decision. So basically what we end up with is 4 primary areas of our bootloader. We have decision-making code here at the beginning. We have our application code. We then have bootloader code. And then finally some code that's associated with resetting our embedded system. Now there are a number of different ways that we can go about making the startup branching decision. One of the simplest ways to go about doing that is to use a simple GPIO pin. In this case, we would put a push button and have it pulled high so that it always shows a maybe 3.3 volts or 5 volts on the voltage rail. So we make that microcontroller input pin set to 1. When we push the push button, it's going to pull that pin down and pull it to 0. So what we're going to do is have it so that if when I power up my embedded system, if I'm holding that GPIO pin, I'm going to load the bootloader. If I'm not pushing that push button, then I'm going to load my normal application code. Now there are some advantages and disadvantages to using a push button to be able to move into your bootloader or not. Some of the advantages is that, one, it can be coded in assembly language. Now, very rarely you'll hear me say that that's an advantage, but when you're developing a bootloader and you're trying to make a very fast decision as to which type of code you're loading, whether you're loading the application or the bootloader, you want the decision made very quickly. You don't want to take tens or hundreds of milliseconds to make that decision. So coding that in assembly language at the bare metal could be a big advantage. Now, secondly, that branching code is very quick. We want it to be fast. So being able to do just a simple push button, that's perfect. All we got to do is do a GPIO read and we can move on. And then finally, we have the fact that it's a very simple implementation. Push and hold the button and you're good to go. Now, some of the problems with using this type of model is that, one, GPIO pins are susceptible to startup noise. So it could be that we misread the pin at startup and think we should load the bootloader when we shouldn't. Two, if we're using a low pin count microcontroller, we have to now use a dedicated pin to be able to determine whether we go into the bootloader or not. So that could potentially be an issue with us from a hardware standpoint. And then third, and probably the biggest factor, is that we could accidentally push this push button and load the bootloader on accident. There's nothing like getting a call from your client or end user saying that they've broken their system, they don't know what's wrong with it, and all they've done is accidentally pushed some hidden button in the system that forces it to load the bootloader rather than the normal application code. Now, let's take a look at some example code that we could write for startup branching using a GPIO push button. This is a very common example that you'll find on most development kits or a lot of example code that's provided by silicon vendors. So it's worth taking a brief look at so that if you come across this type of code, you know exactly what it's doing. Basically, the code is fairly straightforward. The example code I'm going to show is some assembly language code for a Freescale S12X. Something to keep in mind is that assembly language code is going to differ from one architecture core to the next. So this exact assembly language code that's for a Freescale S12X is not going to work on an ARM microcontroller. It's not going to work on a microchip microcontroller or a TI or a Silicon Labs, a Renesas. It's going to have to be customized for any one architecture. So keep that in mind. It's one of the bad points about using assembly language. So what we're going to do here, all we need to do is perform a GPIO check. Is the GPIO pin pulled low, in which case we want to start the bootloader. Otherwise, if it's pulled high, we want to start the application code. So what we're going to do is write some assembly language code to go through and read that GPIO pin. In this case, 0259 is the register address I want to look at. I'm going to compare it to see is it set to 1. If it is, then I want to go, if it's cleared and it's not set to 1, if it's 0, what I want to do is go to the boot code. In this case, I'm going to jump over here, go to boot label, and I'm going to load the stack, go to the top of the stack, and I'm going to jump to the main application for the bootloader. If, on the other hand, it is pulled high, what I'm going to do is I'm going to load the application reset vector. For this particular processor, this requires two different instructions, LDD and LDX, at which case then my application reset vector is loaded, and then I can jump to my application code. So as you can see, this would be very efficient code to make a decision as to whether you load the application or whether you load the bootloader. Just a couple lines of assembly language code, and you're up and running in the application or the bootloader. Now, one of the questions that we should be asking ourselves when we take a look at that example code is, are there any potential flaws with that branch code? Think back to that previous slide. Is there anything that bothers you about that assembly language code? First of all, there's a lot of things that should be bothering you. We have the fact that we're writing an assembly. We have the fact that we have code that isn't portable. We're using a GPIO pin to make a very critical decision as to whether we're loading application code or basically some diagnostics code. So, as you can imagine, there's a number of things wrong. But one of the biggest problems with the code on the previous slide is that we just blindly assume that the application reset vector has been programmed. We're basically assuming that the application exists in flash space when what could have happened is that we have loaded the bootloader onto the microcontroller and we never put the application code, and now no one's pushed the push button and we're going to try to load code that doesn't even exist on the system. This is going to move our system into an unknown and undefined state. So who knows what's going to happen when the system actually boots up. So there's something that we want to do with this assembly language code to make sure that we're operating in a more secure and safe way. So what we're going to do here is we're going to perform a simple check on the application reset vector before we blindly jump to run the application. So we're going to go and we're going to check out our GPIO pin just like we did before. We're going to load the application reset vector if we're told that we want to load the application. And then what we're going to do is we're going to perform this comparison. Now, if we didn't program the application code in the flash space, most likely the flash space is going to be in an erased state, which means it's going to read all Fs. So what I can do if I haven't programmed the application reset vector is I can do a comparison between the application reset vector and all Fs. And if I find that they match, then I know that I have not programmed my application yet, and I should instead jump to the bootloader code and run the bootloader and basically await further instructions. So what we're doing here is we're providing an extra check to make our system a little bit more robust. Now, we could do even more with this. Not only could we check that it's FFFF, maybe we know where our reset vector is going to be located at. Maybe we know what the value of it should be. So we could actually check to see that the value is correct. There's a number of things we could do, or we could check a range of values. But for our example, just performing a basic, simple first check is a good way to go about verifying that our application code exists. Now we can go even further with this code, and we can get rid of that horrible GPIO pin that we want to be able to push a button on in order to go into the bootloader. Pushing a GPIO pin really isn't a production intent solution. It works really good on the bench with a development kit, but with production intent hardware, that's just not going to fly. So what we're going to do now instead is we're going to select either a flash location to store some type of byte information as to whether it's application code or the bootloader, or we're going to use an EEPROM space to make the decision as to whether we're going to go into the application or the bootloader. So there's two ways we can go about doing it. In this example, we're going to look at EEPROM space. We may have some onboard EEPROM, and we want to use that to check to see if the value is set to character B, then we're going to say go into the bootloader. If that location in EEPROM is set to anything else, then we're going to load the application code. So what we're first going to do, we're going to load the application reset vector. We're going to perform a check to make sure that it exists. If it doesn't exist, then just go straight into the bootloader. Then what we're going to do is come in and check that EEPROM status byte. Is it set to B? If it's set to B, then go ahead and jump to the bootloader code. If, on the other hand, it's set to any other value, then we're going to continue loading the application reset vector. We already know that the program exists, so we're going to first check, does the program exist? Yes, it does. Should I be going into the bootloader or into the application code? Maybe it's set to B and we jump into the bootloader. Maybe it's fine and we continue to load the application code. Pretty simple and straightforward, but it's still considered kind of an advanced check from a very simplistic bootloader standpoint. We're adding some additional robustness to the system, trying to make it a little closer to production intent. Now, one of the things I would do if I was trying to create a production intent bootloader, I would also not just have a single character. I'd have maybe a certain string that I was writing and also have some type of CRC associated with it so that I could verify that we just didn't accidentally get a corrupted byte within memory space. All right, so what are some other things that we can do when it comes to starting up the system? We're spending a lot of time talking about how the system starts up because this tends to be a very gray area for developers, especially if they've never developed a bootloader before. What we're going to do is we're going to integrate the branch code into the bootloader so that we initialize the bootloader first, and then once we've initialized the bootloader and our system is in a known controlled state, then we make the decision whether we should remain in the bootloader or whether we should load our application code. Now, by doing this, this allows us to perform a number of extra checks on our embedded system in order to make sure that we're in a good, well-controlled state. It also allows us to perform some special checks for the bootloader that we'll talk about here in a little bit. But the idea is that we've taken this green piece here that was the branching code and we've merged it into the bootloader. And now we have a safe and known state that we're going to load our system into. And then we're going to check to see, does the application exist? Should we go into the bootloader? Should we load application code? Maybe even performing some checks on the system, such as, is the application image checksum correct? Is there a programming tool present that wants to update the firmware? And of course, then we can perform our checks for reset vector. We can do our check for the EEPROM byte, and we can perform any other type of check that we want. So this code allows us then to start performing more advanced checks. And what we can do then is perform these checks. So here's an example of what these checks might look like. So I turn my system on, the bootloader starts up, it initializes the system. I'm in a good controlled and known state. One of the things I'm going to do first is I'm going to go through and I'm going to start performing an image checksum in the background. I want to verify that if I sum up the application space, does it match a checksum that's programmed at the time that the application was. It's possible that the application code could have somehow become corrupted, and I just want to validate that the system integrity is intact. And that is going to take some time. So what I might do is set up a system timer in the background that's going to maybe wait 100 milliseconds in order to allow the checksum to be completed, but also, more importantly, to see if there is a programming tool present that wants to update the firmware. Once the timer expires, we can then perform a number of checks on the system. So for example, we might go through, perform our reset vector check. So is the reset vector not equal to all F's? Is the EEPROM not equal to B? Is a tool present? And is the checksum valid? And if these things in this flow line check out, then we load the application code. If any of these is false or incorrect, then we load the bootloader. And we await further instructions on how we should proceed. And then, of course, it most likely is going to be to update the firmware. So one of the great things about developing a bootloader in this way, and especially using the C programming language, is that the code starts to become very readable, very portable. These are some basic checks that we might want to perform on any bootloader system. So what we can do is we can literally come in here and write some simple C code to perform these checks. So for example, I can check to see, is my checksum complete? Have I summed up all the flash space? And has my startup timer expired? If it has, then I can go through and perform those checks that we saw in our flowchart on the previous page. Then, of course, this is just a simple if-else statement. If these all check out, we load the application image. If not, then we load the bootloader image. Turns out to be pretty straightforward at this point. We're now away from the assembly language code, and we have some very good embedded software code that we can reuse from one application to the next. Keep in mind there may still be some modifications we want to make to this in order to ensure that it's production intent ready, but at least from a basic standpoint, this gives you a rough idea of what you might want to put in your code base. Now, one of the purposes of the bootloader, the primary purpose, is we really want to be able to take application code and we want to be able to update it on our microcontroller. As we talked about before in the requirements section, there's really a couple different ways that we could go about doing this. We really could have a command-driven bootloader where we have the server or some type of laptop and a GUI that's going to be driving the process to update the firmware. So it may be sending a command to erase, sending a packet of data over, waiting for acknowledgement, sending another packet, waiting for acknowledgement. Or it might be totally image-driven. And image-driven is where perhaps the embedded system is capable of downloading the entire application at one time, and then it can update the application on its own without any external influence from any other GUI tools or other devices. And what we're mostly going to talk about today is going to be the command-driven type. The reason is that image-driven bootloaders tend to be pretty simple to develop. All it is download the latest image, store it in memory, and then take that memory storage and put it into our the latest flash location, and then restart, and we've got our latest firmware. Whereas command-driven based bootloaders, these are going to be for microcontrollers that can't store multiple versions of software within its memory space at a given time. So what we have to do is we have to pass it down piece by piece, and in order to make sure that it all gets there properly, it requires a lot of extra effort. And it also makes it more complicated and a little bit more interesting from a software developer standpoint. So we may have a command-driven protocol. It's going to require a couple of different types of commands. The ability to lock and unlock flash space, because we want to secure our flash space after loading an application. We're going to want to be able to read and write configuration information possibly. So we may have it that once we update our application, at the end of line, maybe we want to have a calibration that goes through and we want to write those parameters in the flash or EEPROM. We are also going to want to have image and record data that we want to write. So we're going to take the application image from our PC and we're going to transfer it bit by bit down into the microcontroller. And then, of course, a command to be able to say, hey, if you're in the application, reset it in the bootloader. If you're in the bootloader, reset it in the application code. So it turns out that there's some commands that we're going to want to consider there. And as I mentioned, this is far more complicated to implement than it is to simply have like a thumb drive you plug in, the embedded system goes out and it reads the file on it and updates itself. So image-driven, pretty self-contained, very autonomous, whereas command-driven, not so much. A lot of extra tools we have to develop in order to get that process to work properly. Now, as I mentioned, the bootloader is going to be assembling the image. So if we're command-driven, we can't store the entire application in RAM or flash at one time. What we're basically going to do is chunk up the application and send it down one piece at a time. So what ends up happening is that we've chunked up the application into smaller records, and we're going to send those records over one at a time to the microcontroller. Now the microcontroller is going to have to read in that packet of information, and it's going to have to store it, validate that the packet is okay. It's going to have to then take that data once it's received it, reassemble it into an image block that can be written to flash space, verify the checksum. It's then going to have to write that data into flash space, read it back and verify that that flash space was written with the correct data, and then it's going to have to acknowledge to the tool that, hey, everything went well, please send me the next packet. This process is going to repeat over and over until every little piece of the application has been downloaded to the microcontroller. In the event that anything goes wrong, what you want to do is have the bootloader be capable of knacking or not acknowledging that it was successful, so that you can then have the GUI tool resend the data and then hopefully properly recover itself and store the new data. So as you can imagine, this tends to be just a simple process that is repetitive. So once you get one packet down and you're able to write it, it becomes a repetitive process of just acknowledging and verifying that the data is getting there. Until you get to the very end and maybe you write a application checksum in the flash and then you perform the system restart. Now, as you can imagine, we talked about a couple of different things that we might want to do inside the bootloader, a couple different commands. So let's take a look at what the flowchart for this would actually look like. We might come in from the branching code into our bootloader. We're then going to receive a command. This command is then going to be processed. So we've received the command. Is it to unlock flash space? Probably the first thing we want to do from the GUI tool. So yes, I want to unlock the flash space. Flash space is unlocked. Now let's jump back, wait for a new command to be received. We receive a new command. Maybe it's for an S record. We get the S record, we receive it. It may be that in some communication protocols, we can't send an entire record down at one given period of time. If that happens to be the case, we may need to store individual records in RAM and wait for enough records to come in to be able to assemble one page of flash space. At which point we then have enough data to be able to verify the checksum and write it to the flash space. So once we've received enough packets, we try to assemble them together. We verify the checksum is good. If the checksum's incorrect, we send back a knack to the tool, basically requesting the packets be resent. If the checksum's okay, then we write that data to flash, we acknowledge, and we go back and we wait for new commands on what the bootloader should be doing next. As we talked about, if we're updating firmware and we're at the S record point or the point where we're writing application code, we're going to repeat this process over and over and over again until all the application code's been written to flash. At that point, we may decide that we want to send a command to write configuration data, such as erasing the EEPROM and writing configuration data, or perhaps the final command we would receive, which is to move into the application space, at which point we reset the processor, we load back into the area where we're going to make that branch decision, and if everything has gone smoothly, then we should be able to load the application code. Now, one of the questions that often comes up at this point is, how do I reset my microcontroller? And as it turns out, there are a number of different ways that we can reset the microcontroller after we've updated the firmware, or when we're trying to go from our application to our bootloader. The watchdog timer is probably the most basic way to restart the system. And there's a number of ways that we can use the watchdog timer. The first is that we need to enable our watchdog timer inside our application code and inside the bootloader. We need to make sure that we integrate the watchdog timer petting routines, which make the watchdog happy and not reset our system. We need to make sure that they're tightly integrated into the bootloader and or the application code so that it isn't a useless watchdog timer. And basically what we're going to do is we're going to enable the watchdog. And one of our options is to, when we want to reset the system, just go into an infinite loop. Don't pet the watchdog anymore and just wait for it to time out, get angry, and reset the system. Now, the second method, which is a little bit more controlled, is to illegally write a value to the watchdog pet register. Many microcontrollers have it so that if you write an illegal value to that register, it assumes something has gone wrong and will immediately reset the system, which is a great way to do it. And then the third option is, of course, some watchdog timer peripherals allow you to perform a soft reset. And it's just a command that you issue to the watchdog peripheral, and it performs the reset. So that's a very useful way to do it. You'll find that some parts are very complicated. They may have multiple watchdog timers. You may have the ability to do a soft reset, which won't change the state of any of the peripherals or the RAM. There are some that offer you a hard reset option, which basically is powering off the microcontroller and powering it back on. You have to read through the data sheet in order to see what the capabilities are of your watchdog timer. A production intent bootloader isn't going to, at the end of the bootloading process, turn on a light or issue a message that it is now safe to restart the embedded system, and please do so now. Because we have a watchdog timer on board, we can completely automate that process so that once we are done updating the firmware, we just perform that watchdog timer reset, the system resets, and then the application code comes up and runs the latest version of code, and the user knows that, hey, my system's working the way that it's supposed to. What some example code might look like in order to reset the watchdog timer, we could create a very simple interface here that's watchdog timer, this is the subsystem, underscore, and then the function that we want to perform, in this case resetting. You can see here all we're doing is entering an invalid key to force the software to reset the system. So a lot of times these watchdog reset routines, very simplistic, not terribly complicated, which is good because the rest of the bootloader system can itself be fairly complex. One of the things that you've probably been wondering is, I have this application code, I have this bootloader code, I have reset code. Where does all of this stuff go in memory? And one of the things that we have to do as developers is we have to partition out memory on where we want these different pieces to be located. So a typical memory map is going to be completely filled with application code. It's just going to be application all the way through. Maybe we have some boot configuration areas or some configuration bits we need to set. But for the most part, we have our reset vector, interrupt vector table, and an application code. But now we have this bootloader, which is really a completely separate and second application. So what we need to do is partition memory so that we can have two applications in memory at one time. And this literally requires going into your linker file and mapping out where you want the code to go. So for example, we want our bootloader to be the first application that starts at startup. So we're going to have our application, we're going to have our bootloader reset vector located at the reset vector location for the hardware. We're probably going to put our interrupt vector table for the bootloader right after that. And then usually this first area of flash space, usually you can protect this area of memory. So that makes it a very good place to put a bootloader. Because if I put a bootloader there and I lock that area of flash space so it can't be written to, that means I can protect my bootloader so that if something goes wrong during the firmware update process, my application becomes totally corrupted, all I need to do is restart my system, and I know that my bootloader will detect that something's gone wrong, and it will boot up. If I allow the option for my bootloader to be updated, or I don't lock down this area of flash, if something goes wrong during the process, you never know. You could end up with a corrupted bootloader, at which case it could be that the system won't be recoverable, and you've essentially just bricked a perfectly working embedded system. Now, depending on the type of system you're developing, it could be that you're now throwing away a $20 board, or it could be that you're throwing away thousands of dollars of hardware simply because you made a mistake developing your bootloader. So keep in mind, you want to try to look in your data sheet to put this in a secure location where you can protect the bootloader. Then the application code, we can literally put the application reset vector and vector tables anywhere we want in memory. We can put the application anywhere we want, and then we can put the application checksum wherever we want. We just have to go into our linker file and specify where those locations are at, and then the bootloader needs to know where the application reset vector is so that when it decides it needs to load the application, it knows what memory address it needs to dereference in order to start the application code. Keep in mind that flash space usually is not indivisible down to the individual byte either. Typically what you find is that flash space is organized into pages and sectors, where a page is usually the smallest number of bytes that you can erase at a given period of time. So you may find that 256 bytes is the smallest amount of flash space you can erase at a time, or maybe even a sector is the smallest amount of size that you can erase. Sometimes flash controllers only have a sector erase, which means if you're going to erase something, it's 4K of byte space that you're going to erase. So you need to really dig into the data sheet for your flash space as well. The reset vector, which I've been alluding to on the previous slide, it may be that you're not very familiar with what that actually means. So the reset vector is basically just a location in memory where the first instruction for the application is located at. So what happens is the microprocessor starts up and it loads the address that's stored at the reset vector, and then it starts executing instructions from that address. So there's a couple questions that we really should be asking ourselves as developers. How many reset vectors are now in memory? If we have a bootloader and an application, we've got 2. But we could have an architecture for a bootloader where we have the bootloader, an application code, original factory firmware application, and then maybe we even have application buffer space. So it could be that we have anywhere from 2 to 5 reset vectors now that we're going to have to manage inside the memory map. Now that we have more than one, we need to know where they're located at and what they correspond to. That way the application knows how to reset back to the bootloader, and the bootloader knows what area it needs to dereference in order to run the application code. And then finally, we have to ask the decision of how should the reset vectors be located? So where should we actually put them at? A lot of times it doesn't matter. You can make that decision and you simply go into a peripheral and change it within the microcontroller. But you really need to dig into your data sheet to answer some of these questions. And then of course, once we've decided on and answered these questions, we go into our linker file and we are going to provide it with the address for where the reset vector is. So if I go into the bootloader, I can say the application reset vector is located at, and I provide it the address, how long it is. In this case, it's 2 bytes worth of length. And I know that if I go into dereference this address, that I'm going to start the application code. And it could be that I have application 1, application 2, application 3, and so on and so forth. Keep in mind as well that one of the things you want to do with your application linker file is make sure that you don't let it know that the bootloader area exists within memory. So what you would do when you create your application linker file is delete the area of memory from the linker file that's associated with the bootloader, so that way you can't accidentally generate code that wants to be located within the bootloader area of memory. Alright, and then the final topic that we're going to talk about today is some of the file formats that we can use for our application code. We could have an entire full webinar just discussing these different file formats, how they behave, best practices with them, how to convert from one to the other. For this webinar, I just want to make you aware that they exist. So for example, we have a couple of different record formats we can use. We have Motorola S records, Intel hex file format, common object file format, and binary file formats. Our application from our IDE, usually you can generate any of these or at least one of them, and then we can write our GUI code to go through, parse this, send it down to the bootloader, and then these records are basically going to tell the bootloader what our application is and what the pieces are and where they should be located. So let's take a look at this S record example. So a single record is a single line here within a file. What you find is that you have a header and basically a footer at the end for each application. And then the information in between is your actual application code. And what you find is it's broken up into an area for address space, which is basically going to say, hey, the data associated with this record is going to be located at address location, maybe hex 80,000. And then you're going to have, here's all the data that goes at that address. And then you have a checksum associated with that. So the idea is that we could send each of these records down one at a time. The bootloader will take the record, see whether it's a header, a footer, or a data record. It'll see how many data bytes are associated with the record, where do they go at inside my flash space, and then it will have the data, and it can verify using the checksum that the data is valid before it ever even begins to write it into the flash space. So this ends up being a very good way to break up the application into smaller pieces and then send it down to the bootloader. We may even take these S records, or one of these record formats and put a packet of data around it. So this may be data that we're sending, but we may have a command out front associated with it. We may have a CRC again even further back. This could be packetized into a more robust format in order to allow the bootloader to know what's going on and what stage it is in the bootloader. We may find that we want to tell the bootloader how many records to expect, and maybe we want to provide a record number for each of the different records that we're going to send down, in addition to any command and performing additional checksumming. So just a couple of ideas on how we can go about creating an even more robust bootloader. Now, one of the questions is, now that you have a basic understanding of a bootloader, what it does and some of the pieces that are associated with it, where do you go from here? Now, there's a couple different things that we can do. First of all, I have a couple of resources available on my website at Beningo.com that would be very useful for you to develop a bootloader. The first, I have some C Doxygen templates that are free, that basically document different interfaces. You can go out, grab those from my website. Great way to just document your embedded software. Secondly, Embedded Bytes newsletter. I periodically talk about bootloaders and robust design techniques. A lot of great tips and tricks are in there. You can go out to the website, sign up for that. Third, I do also have a white paper that I put together on bootloader design techniques. So it goes into a little bit more depth on all these different pieces to provide you with a little bit clearer picture on where you can go to really design your own bootloader. Once again, that's just under www.beningo.com. You go to the blogs area and you'll see that there's a white paper tab. You go to white papers and you'll see it there on bootloader design techniques for microcontrollers. And then finally, you could go out and you can read a number of different application notes that are on bootloader design. Usually what you'll find is you have to read a whole bunch of different ones in order to really get the full picture. A lot of different white papers just focus on core pieces, or they tend to be very focused on just the functional aspects and not necessarily how you design a production intent robust bootloader. Then the final piece is that I also perform a number of bootloader design techniques workshops that you could also attend. They're online and in person. So if you have a bootloader that you're looking to design, you could attend the course, and we would walk through the entire design process, hands-on, developing a bootloader from scratch. So that would provide you with some basics on how you could go about this in more detail. There's also a bootloader toolkit that I've developed that is available. If that's of interest, you can email me just using jacob@beningo.com. And then, of course, as I mentioned, I've created dozens of these bootloaders. So if you're looking to get one developed quickly, you can email me and let me know what your requirements are, and we can discuss how to get that going. So I appreciate your time and attention during today's webinar. If you have any questions or comments, please feel free to contact me. You can just reach me at jacob@beningo.com. There's a number of different ways you can get a hold of me. So they're here on this slide here in this column under social media and contact. You can contact me through social media or through my email address. Then here's the links and QR code for the newsletter, and then some additional training efforts that I go through. So I appreciate everyone's time and attention and look forward to talking with you further in additional episodes.